integrator. So that is the basic Opamp integrator circuit. You can notice the resistor in inverting amplifier circuit is replaced by capacitor here. So that is very basic circuit, and we will find the output for this circuit. We can determine output in two ways, through time domain or through Laplace domain. We will show the both this analysis. So for the first analysis is first analysis through time domain. So through time domain analysis we will find the output voltage. So in this case I'll assume that current through R is I1 and current through capacitor is IF. Now from KCL we know summation of these two currents. Input current of the op-amp is 0, input current is 0. So summation of the I1 and IF is equal to 0. IF plus I1 equals 0. Now I1 is the Vx minus Vi by R. So current through R. So I1 is Vx minus Vi by R. So let me write the I1 first. Vx minus Vi by R. That is the I1. Now IF is the capacitor current. Capacitor current and voltage are related by I is equal to C dV dt. So capacitor current and voltage are related by I equals C dV dt, where I is the capacitor current, V is the potential difference across the capacitor. So in this case you can see current is flowing in this direction. So I'll assume capacitor that is plus, that is minus. So capacitor current can be written as C, that is C d dt of the capacitor voltage. So capacitor current is C dV dt. So dt of capacitor voltage is, this point voltage is Vx and that point voltage is V0. So it will be Vx minus V0. So that will be the capacitor current. It will be equal to 0. So that part is the current through R and that part is current through the capacitor. Now we know this kind of connection is a negative feedback connection, and in this situation we already discussed that will be the virtual ground. As a result, you see the Vx will be 0. So I'll replace Vx by 0, replace Vx by 0. As a result, you will get that dV0 dt equals minus Vi by Rc. So you can write this dV0 dt equals minus Vi by Rc, or you can write V0 equals minus 1 by Rc 0 to t Vi dt plus some voltage, that is V0 0. Now see, you can write V0 in terms of this integration form, but that part is the initial capacitor voltage. That part is due to the initial capacitor voltage. If I assume that capacitor is initially discharged, capacitor is initially discharged, then we can write V0 equals minus 1 by Rc 0 to t Vi dt. So that will be the output. So you can see output is the integration of the input, and there is a factor, that is 1 by Rc, that is the slope of the integration, and this minus sign, due to this minus sign output will be inverted integration. So that's why this kind of integrator is known as inverting integrator. That is known as inverting integrator. So that was the method 1. In method 2, that is we can get the same kind of expression using method 2, which is through the Laplace. Method 2. So in this method, what we'll do, we'll replace each element here in Laplace domain by Laplace domain representation. So capacitor in Laplace domain, equivalently we can write it is 1 by SC, R will be R, and V will be capital VI, V out will be capital VO. So this VI, VO are the Laplace domain voltages. So you can see, you know this kind of circuit. It is like the inverting amplifier. Gain of the circuit will be minus this by this. So V0 will be equals minus this part by this part, 1 by SC by R into VI. So that will be the expression equals V0 equals minus 1 by RSC VI. Now if we take inverse Laplace, or you can write minus 1 by RC VI by S. Now division by S in time domain is equivalently the integration of the signal. So V0t, notice here that is the Laplace domain V0 and that is the time domain. So inverse Laplace transform of this equals minus 1 by RC 0 to t VI dt. So that is the Laplace domain VI and that is the time domain VI, sorry, small VI. So that will be the same expression for the integrator. Here we have assumed capacitor is initially discharged. So assume capacitor is initially now why we do the second method, we can get the same expression, that expression and that expression are the same. Still sometimes we prefer the Laplace domain representation, because in Laplace domain the differential equation solve will be very simple. So that's why we'll do the capacitor and integrator based circuits. We convert this capacitor and integrator by circuit in Laplace domain, and we do the analysis. Now second, so these are the inverting integrators. In second, we'll discuss the non-inverting integrator. This is the circuit for non-inverting integrator. In this case, we'll analyze the circuit in Laplace domain and find the output expression. So Laplace domain capacitor will be here 1 by SC. This capacitor will be same. Here you have R. Assume that this input is represented in Laplace domain, output also represented in Laplace domain. So first find this voltage potential, that is node A, that is node B. This node A potential and node B potential will be equal, which we have already discussed. Now see, First find node A potential. You see that is a simple potential divider, because we are assuming capacitor resistance is 1 by SC in Laplace domain, or impedance is 1 by SC in Laplace domain, and you have R. So this node A potential will be VA equals, it will be VI by total impedance R plus 1 by SC into, so that will be the current. So this current will be VI by R plus 1 by SC. So that will be the current through this, and the potential at this point will be drop across this, signal drop across this. It will be multiplied by 1 by SC. Or you can write VA equals VI by 1 plus SCR. So that will be the A node potential. Next, we know from non-inverting amplifier analysis that if this node potential is A, that node VA and VB will be equal. VA will be equal to VB, and you see here you have element which is 1 by SC, here you have R. So from non-inverting amplifier we know VO output will be equals 1 plus RF by R. In this case RF is 1 by SC. So non-inverting gain was 1 plus RF by R. In this case the gain will be 1 plus this by this. So 1 by 1 plus SC by R into VA equals, so if I replaced VA here, so it will be 1 plus RSC by R into VA will be divided by RSC. VA will be VI by 1 plus RSC. So it will cancel out, and VO will be equals 1 by RC into VI by S. So you know division by S equivalently integration in time domain, or you can write VOT. So we are taking the inverse Laplace transform. VOT equals 1 by RC 0 to T VI dt. So this VI is time domain potential, and the same assumption is valid here, that is capacitor is initially discharged. So here you can see the integration slope is 1 by RC. Integration slope is 1 by RC, and there is no negative here. So that's why it is known as non-inverting amplifier integrator.